With the ever-increasing data rates, the question keeps coming up if coherent transceivers are actually inevitable even in the metro distances of up to 80 kilometers. Is that really the case? If you want to find out, stick around and we'll check it out. To be able to answer that question, we first need to have a little look in the technical aspects of these different technologies. So let's start off with the normal transceiver, in other words, the so-called direct detect transceiver. It uses a so-called NRZ, so non-return to zero binary code. What that means is it has two states. It has a 0 and a 1 state. Now, to be able to qualify the quality of the signal, we have a look at the so-called eye diagram. Let me explain. So what you see here is an eye diagram of an NRZ signal. And basically what an eye diagram does, it takes this code here and it chops it up into little pieces and continuously overlays it. So if I would draw this signal here onto the eye diagram, what it would actually look like is I start at the 0 state, I go up to the 1 state, continue on the 1 state, go down onto the 0 state and go out on the 0. Now here the next stage is I continuously go onto the 0 state. After that I go from the 0 state up to the 1 state and across, and then I carry on 1 state all the way through, and that just overlays it the whole time continuously. And what then happens is then what you can see here, we have this so-called eye in the middle, and that eye needs to be open. And what that means is when the eye is open is that the transitions between the 0 and the 1 state and vice versa are accurate enough for the receiver to be able to detect the signal and to be able to interpret the signal. We have another technology for direct detect transceivers, and that's the so-called PAM4. And what that means is instead of 2 states, we actually then have 4 states. And that is great because we are able to code much more information within the same period of time. However, there is a downside to this whole thing, and that you can see here, because with the 4 states, we also get 4 transitions, meaning we've got a triple eye. Okay, now let's talk about coherent transceivers. Now, coherent transceivers, just like PAM4, can also use multiple states. But in addition to that, it also uses signals in different phases. So in other words, in simple terms, instead of the signal just going up and down to have the different states, there's also a signal that, for example, goes from left to right to depict those different states. Now, that by far is more complex and much more sensitive also to degradation. And that's why at the core of coherent transceivers is the so-called digital signal processing units, in short, the DSP. And that DSP actively compensates the signal degradation. Now, before I go into more detail of that, I want to talk about that signal degradation and the different types of signal degradation. Let's have a look over here. The first type of degradation we're going to have a look at is the so-called attenuation. And what the attenuation basically is that while the signal is being transported over the fiber cable, energy is being actually taken out of that signal. And the effect that it has on the eye you can see here. So when you start off with a nice amplitude, the eye is really nice and big. However, if the attenuation increases, the eye actually gets smaller and smaller because the amplitude of that signal also is much smaller. The other degradation I want to talk about is the so-called dispersion. And what the dispersion basically does is it introduces a jitter, meaning that the transitions between the different states aren't as clear as they were before, and that you can see the difference here. So this is a signal, a PAM4 signal without jitter, and this is a PAM4 signal with dispersion, so a lot of jitter in there. And as you can see, the eye diagram isn't really visible anymore. So now we've had a look into these different technologies, and we also had a look into the types of signal degradation. So the question really is, why not just use coherent the whole time? Because, I mean, you can transmit much higher bandwidths, you can go much further distances, because it actively compensates the degradation. Well, the point is that to be able to do that, it actually then has that DSP, which comes at a cost. I'll show you why. So this is a simple setup of a direct detect receiver, and it just has a photodiode, an amplifier, and a clock data recovery, and that is pretty much it. Now, the coherent transceiver, on the other hand, is by far more complex. It's got this whole area here at the front to handle the different phases, and of course, it's got the so-called DSP. And the DSP basically is a computer, a very small one, but it is a very powerful computer. And that computer uses a lot of power, and it is also very expensive. So if we compare direct detect and coherent transceivers, you actually see that the characteristics and the key parameters are actually invert to each other. So to answer that question, are we going to be using coherent transceivers even in that metro area of 80 kilometers and less? Well, the answer is maybe, maybe not. Because let's have a look at this graphic here. If you're using high data rates and long distances, of course you're going to be using coherent transceivers because direct detect won't work. However, when we're talking about the shorter distances, even at higher data rates, the direct detect technology is still the most efficient way to go. However, we do have this transition area where it isn't very clear. So sometimes it is better to use coherent and sometimes it is better to use direct detect. And the point is, this transition area is constantly shifting because technology is evolving on both sides for coherent and for direct detect transceivers, and also costs are going down. So there is not that one clear answer, and it very much depends on the application. I hope you learned something today and you liked this video. Please leave a comment. Also, if you have something to add to this topic, because it is a very interesting topic. So thanks for watching and hope to see you next time. Bye-bye.